Curve sketching. I'm sure you have always been wondering how people do this. I give them a function and then they just sketch it. They just kind of see how the function looks like. But there is systematic behind this, and this is what you would like to learn in this video today. So to properly sketch a function, you need the function, of course, but you also need the derivative f prime of x and the second derivative f double prime of x. From f we can learn many things, for example the domain. We can identify where f is 0, which are the intercepts, and then we can look where f is positive or negative, or if it has singularities, where f might not exist, which we call DNE, does not exist. Then there are more properties which we can find from f. For example, if trigonometric functions are involved, then f might be periodic. Or we could have symmetries like even or odd functions. And finally, we could even have some asymptotes which we can make out. So these are all properties which you can directly find from the function f or from a given formula for a function f. Now to the derivative. So what can the derivative tell us? Well, we learned that the derivative is the slope of the tangent line, right? So meaning if the derivative is positive, the function increases. If it's negative, the function decreases. If the derivative is 0, then the function could have minima or maxima or a saddle point. So if the derivative is positive, this means that f is increasing, and if it's negative, this means f is decreasing. And then we can have special points where the derivative is equal to 0, or we can have points where it does not exist. And then in this case, those points are called critical points. And we have seen earlier that critical points can arise as local maxima or minima. And then, finally, we have the second derivative, f double prime. But we have not yet discussed what f double prime stands for. So I go to the next slide and I explain a little bit about the second derivative, and then I come back to this slide to complete this summary sheet here. So f double prime stands for concavity. And we define concave up, concave down, and inflection points. So how does this work? For example, let's look at the second derivative if it is positive. So this means that f prime, okay, one derivative less, so that f prime is actually increasing. So try to visualize this. F prime again is the tangent line, so the slope of the tangent is increasing. So this could look something like this. So I plot a few little tangent lines, and the slope is increasing, so they're getting more and more positive, or here from negative to positive. Now if I plot a curve which has those tangent lines, the curve could look like this. So the curve touches the tangent lines, and a function which is curved like this, a little bit like a smiley face, this is called concave up. And this is actually a good way to memorize the things. So f double prime positive means we have a smiley face. Something is positive, so we are very, very happy. Concave down is very similar. So when the second derivative is negative, then f prime is decreasing. If I do again my little trick with the tangent lines, so this means like following. So I have maybe first positive slope, but then I get tangent lines which decrease and might become even negative. Now plotting a function through these could be, which is tangent to the tangent line, something like this. So this gives a sad face. So second derivative negative is a sad face, which is concave down. So that's a way to remember these kind of things. So happy face, concave up, sad face, concave down. Now inflection points are those points where the second derivative changes sign. Right, so this could change from positive to negative, or it could change from negative to positive. Okay, so let's go back to the previous slide and then add what was missing. So f double prime positive, this means f is concave up, so happy face. F double prime negative means f is concave down, so that is the sad face. Okay? And then we could have inflection points where this changes from one to the other. So now I claim if you compute all these things, you start with f, then you go to f prime, then you go to f double prime, identify where these functions are positive, negative, if they are periodic, if they do not exist, all this stuff, then you are able to plot any function which we give you. Anything. Yeah, but it looks like a lot of work, doesn't it? So we have to go through all these steps to be able to plot a function. So let me show you how this is done on an example. So here we have the function f of x is x squared plus 8 divided by x. So by looking at it, this is not kind of a standard function. So by looking at it, we do not know how it looks like. So let's start with what we learned. Let's start with the function f. And so first of all, we need to find the domain. Yeah, I can sub any number except 0, right? So that's easy. Domain is all real numbers, but it cannot be equal to 0. Or you could say f does not exist at 0. Okay, so we have already a D and E point identified, which is at 0. Now let's look at the intercept. So f of x is equal to 0. Okay, so this means x squared plus 8 divided by x is equal to 0. So I can multiply this by x, and I have x cubed is equal to minus 8. And then I can solve this, and I get x is the third root of minus 8, and this turns out to be minus 2. So x minus 2 is a root of f, or is an intercept of f. So f at minus 2 is equal to 0. Now this we can indicate in our graph and make a little dot at minus 2. Let's look for asymptotes. If I consider the limit, we notice that at 0 the function does not exist. So let's look at the behavior as x approaches 0 from the left and from the right. If I write down limit x goes to 0 plus, so from the right, x squared plus 8 divided by x, then the x squared term will be super small. And the 8 over x term will be super large, and it will be positive. So this is of the form 8 divided by epsilon. So then this goes to plus infinity. And the other limit, x goes to 0 from the left, x squared plus 8 divided by x. Now here again the x squared term is really super small, but the 8 divided by x term is really super big. But now x is negative, so 8 divided by x is also negative. This is of the form 8 divided by minus epsilon, so this goes to minus infinity. So we have a vertical asymptote at 0. And the function comes from here somehow, and then it comes from here as well. So these are things we found from the function f. Now we can look at intervals where f is positive or negative. To understand where the function is positive or negative, I do a little table. I have two special points. F at minus 2 is equal to 0. So this is f of x. And f at 0 does not exist, d and e. And then I'm interested what happens between those points, or left or right of those points. So this is the interval x is less than minus 2. And here we have minus 2 less than x less than 0. And here we have x bigger than 0. Now let's look at x is less than minus 2. So x is negative, and now take a really huge negative number. And then look at the function. So then this term is really, really huge and positive. This term is really, really small and negative. So together, this will be positive. So we make a big plus here. In the interval minus 2 less than x less than 0, in this case, let's say x is close to 0, then the 8 over x term is really big negative. The x squared term is really small. So here this term is negative. And then if we go beyond x, for x positive, well, x squared is positive, 8 divided by x is positive. So this is certainly also positive. So we make a little table for f, where we indicate plus, 0, minus, d and e plus, depending on the function is positive, or 0, or negative. In the graph, so we know now here the function is positive, here the function is negative, here the function is positive. And that's basically all we can find from the function itself. So now we should move on to the derivative. So if f is x squared plus 8x, then the derivative f prime is of course 2x minus 8 divided by x squared, using the power rule for the differentiation. And again, I'm interested where is f prime, positive or negative, so that I can find the monotonicity. I know where it's increasing or decreasing, or where are the critical points. Oh, critical points. So then we know already f prime at 0 does not exist, because you cannot divide by 0. But where is f prime equal to 0? So let's compute this out. Then we have 2x cubed is equal to 8. So x cubed is equal to 4. So x is the third root of 4. Third root of 4, this is a little bit less than 2, so this is about here. So there's the third root of 4. Okay. And where is f prime, positive and negative? Well, let's do our little table again. So we have 0, and then we have the third root of 4. And here we would like to know f prime. And then underneath, I'll show you what it means for f. So then we have x is less than 0 here, and then 0 less than x less than third root of 4 here, and then x bigger than the third root of 4 here. At 0 we have a d and e, wonderful. At third root of 4 we have a 0. Good. So now what is for x is negative? If x is negative, then simply both terms are negative, right? So minus, between 0 and the third root of 4, we have 0 is rather small. So the first term is positive but small. The second term is negative and big. So this is also minus. But then beyond this point, third root of 4, we have that 2x will become big and positive, and the other term is small and negative. So it's positive. So these kind of arguments take a moment to digest. So if you like, stop the video and think about this yourself and see if you get these minus, minus, plus signs on the right position. For the function f, this means that f is decreasing here. It is also decreasing here, and it is increasing here. And now we had this rule that if the derivative changes from decreasing to increasing, we must have a local minimum. So that's what happens here, local minimum. So going back to my curve, so here is somehow a local minimum. Now let's add what we know from f. F comes from here, goes to this point. We got a little bit more information. Now let's look at the second derivative and at concavity. Second derivative, so here's a derivative, 2x minus 8x squared. The second then is f double prime is 2 plus 16 divided by x cubed, okay? And then again we know that f double prime at 0 does not exist. Same thing, we can't divide by 0. And let's see where is f double prime equal to 0. For 2 plus 16 divided by x cubed is 0. This means 2x cubed is minus 16. X cubed is minus 8. X is minus 2. Actually, that's the same point we had before. So right here. Okay. Let's also make a table for f double prime. Then we have x is less than minus 2. We have minus 2. We have minus 2 less than x less than 0. And we have x bigger than 0. And now we want to know f double prime and also what it means for f. Okay. I forgot 0. Sorry. So then include a 0 here and then x bigger than 0 here. If x is less than minus 2, we are very, very negative and very big. So this means here the x cubed term is 1 over x cubed term is very small negative. The 2 is bigger, so we get a plus. At minus 2 we are 0. And then between minus 2 and 0 we're getting close to 0. So then the 16 over x cubed will be huge and negative. So it's a minus. At 0 we have a dne, and for x positive we have something positive, so we are plus. Okay, so for f this means plus. What was plus again? Concave up, so a happy face. So this is this. And here it is the other way, it's a sad face, and here it's a happy face again. So how can we combine all this information? So in red is the information we had before, and now let me add something what we learned from the second derivative in blue. So maybe here. So here we curve like that, which is part of a sad face. Here we curve like a happy face. And here we curve like a happy face all the way. So this would be my guess for the function. Shall we plot it? Shall we have a look how it looks like? Okay, let's plot it. Here it is on the right. And you see, indeed, we have concave up on the left. It changes to concave down at -2. And then right of 0, it looks a bit like a parabola, so it is certainly concave up. Minimum value somewhere here. It has a 0 value somewhere here. And it has the asymptote. So we did a very good job. We got a very good picture without using any computers so far. So here I summarize the 3 tables which we used. We had a table for f, we had a table for f prime, and we had a table for f double prime. And for each table we identify the critical points where something happens. Either we get 0 or we get dne. Okay, so here it happened here, and here. And then also we identify the areas in between, because we would like to know what happens in between. So as promised, it is a bit of work, but it's also worth it because you get a beautiful understanding of a function. So let me summarize. To sketch a given function, you really do need f, f prime, and f double prime. The function f tells you something about the domain. Positive, negative, intercepts, does not exist points, or it could be even or odd or periodic. The derivative tells you about increasing when the derivative is positive, or decreasing when it is negative, or critical points where f prime is 0, or f prime does not exist. And then finally the second order derivative tells you something about concave up if f double prime is positive, concave down if it is negative, or where f double prime is 0 we could have inflection points.